it's 2 days after yesterday, which means it's Saturday. That makes so much more sense in my head than I actually said it out loud. If you remove 28 days from any month, you get a couple of days left over, 2 or 3 days left over. You can add that to the day before the beginning of the month, and then you will be able to figure out what the end of the day is, end of the month. In this case, since today is the beginning of the month, yesterday was Thursday. It's 30 days, so add 2. Thursday, Friday, Saturday.
I slept last night.
I didn't.
I slept for a whole 4 hours. I've slept 4 hours this week.
My roommate...
I slept last night.
My roommate went to Hamilton and decided to stay out after going to Hamilton for an extra hour. Came back at midnight and then was like, oh yeah, I'm sorry that you had room inspections on. I only picked up my laundry. What?
Well, I guess
Did he actually have homework or no?
Yes.
Okay.
But it wasn't that. It was homework for ModPhysb, which means it wasn't necessary.
I understand.
No, but he can still tell if you click on it, and you're still morally obligated to do it, especially since like everybody failed the quiz.
Unless it's Janice.
Ethan's not going to be here today, so there's going to be enough room for everybody. He has bronchitis. There's a stool here.
Here. A little bit of
Don't ruin this stuff. I will murder you.
Just hit you with stick.
God, you sound like my parents.
Oh, I feel too high up like this. It's odd.
Yeah, get off your height. It's only at the top, isn't it?
Yep. It is more. Document
The sadness when someone's for fragments.
I don't want to be alive.
Yeah.
So I don't want to be alive.
Yes.
You're in a world where something depends upon like
You like white?
I do?
Yes.
What evidence have you of this?
you done any other?
That's a wallet.
Good point. You have money in that wallet.
I don't.
Well, then what's in the wallet?
My ID.
Alright, number 1.
Well, then that means you have something.
Assume you use the bomb exploding at the origin. If you didn't, there will be a shift on everything that will not affect the distances between things. The differences between coordinates, okay? But if the bomb's the origin, that's 0, 0, 0, 0. The light would be 2 seconds, 10 light seconds, 0, 0. For number 2, it would be negative 0.3 C. For number 3, the bomb would still be 0, 0, 0, 0. The light would be, sorry, I don't have this in exact form. The light would be 5.24 seconds, then 11.1 light seconds, 0, 0.
5.21.
Why is he talking to me?
Benji, you're getting all this, right?
No. I'm bothering to actually solve it
Okay.
myself.
This is actually not the one I want.
Dancing parties.
Number 4 is L over 2C. And number 5 is, there's a few different ways you can write it. I have LV over gamma times V squared minus C squared. But there's a few other ways you could write that because of the form of gamma.
What did he say?
LV on the top, and the denominator is gamma times quantity V squared minus C squared.
V squared minus C squared.
Okay. Number 6. Let's assume you use the neo-link as the origin. If not, it kind of flips things around and doesn't change the answer. Neo's the origin 0, 0, 0, 0, then Giscard is 0, D, 0, 0. Then number 7, to Neo still 0, 0, 0, 0. Giscard would be, sorry, I don't know the exact number again, negative 0.314 D over C for the time, and then 1.05 D for the position. 0, 0. Therefore, 8 would be Giscard. And 9 is Magdalena. Okay. Questions Well, I'll get to 9. Let's do the other part first. 5. Oh, this one's
Go to the Google Doc and fill in what answers you have. I have some answers too, so maybe if we put it all together, we'll have all of them.
I didn't hear you.
Go to the Google Doc and fill in what answers you have. I have answers there too, so maybe read all of them.
Okay,
the
maybe.
man standing in a train. The train moves this way relative to the Earth. He is standing in the center of the train, fires the light beams out to the two ends where they explode, because everything explodes. The reason these are explosions, because explosions have a kind of definite time and position, so those are events that are sensible. Okay, what should we use as the origin here? We're going to do this Lorentz transformation. What should we use as the origin? Okay, the man firing the light, that's one possibility. Let's go ahead and do that. It's actually not the easiest one to use, but it's fine. Then the left-hand light would be, how big is the train again? Oh, L? The whole thing is L? Okay. So the left-hand light would have position coordinate negative L over 2 in that case, right? And how much time would it take to go negative L over 2? Or, yeah, go L over 2. We know that distance equals velocity times time, so time equals distance over velocity, right? So therefore, it has to go L over 2c is how much time it'll take to reach there, right? Because L over 2 is the distance and c is the velocity, this light, okay? And then the distance coordinate, position coordinate would be negative L over 2. Okay, the time coordinate is positive, of course, because it takes a positive time to go there, but it's negative position coordinate, right? This one over here would be the same thing, except it would take the same amount of time, it's going the same distance, as positive L over 2. Make sense? Okay, so those coordinates. Now, the question was how much time between? Okay, so in the bomb frame, how much time between, for example, you would take the difference between the two time coordinates, and you would get 0. Okay? Now, this is all in which reference frame? The what? The train's reference frame. Say, the man or the train, they're the same reference frame. We want to know about the Earth's reference frame, right? Okay, good. So when we want V is the velocity of what?
The reference.
Yes, I know. Which reference frame? V has to be the velocity of which reference frame? The Earth's reference frame. It's always the velocity of the reference frame that you want to know. Velocity of the reference frame you're going into, right? So V is the velocity, in this case, of the Earth, because the Earth is the one we're trying to find out about. The Earth is the frame we are transforming into. So V is the velocity of the Earth relative to the train. What is the velocity of the Earth relative to the train? Positive or negative? Positive, good. Because the train is moving left relative to the Earth is moving to the right relative to the train. So therefore we get positive V. Okay, it's a positive number. Great then. So now what we have to do is do a transformation on these coordinates. So let's find what t prime is. Right now I'm just going to write gamma. We don't know how to find gamma, so I'm just going to write this as gamma. So the t prime is going to be gamma times both. I'll just rewrite the equation so you can see it. Right? That's our time coordinate. Transforming this 4 vector means I take gamma times the time coordinate is L over 2c minus v over c squared, and here's the x coordinate, negative L over 2. Okay? Working this out of it, you get gamma times L over 2c minus VL over c squared over 2c squared. And again, you can simplify that a little bit, but actually maybe we should simplify it a little bit. You can factor out L over 2, c, actually, and that gives you 1 minus v over c. Yes. Thank you. No blood hands. Okay, good. Thank you for catching that. Yes. Good question. Good. Keep going. All right. Any others? Good. Dr. John can't do math anymore. That was back to the old days. And so I need you guys to help me out. Okay, good. So this looks okay now? Good. All right. So we could also calculate the x-coordinate if we wanted to, but I don't think we need it for this particular problem, right? The problem's asking about times. Yes. So that's a hint. If you only need to know about times, you can save yourself some trouble and not calculate the x-coordinate transformation, right? Okay, that was for this guy, right? This guy has a different transformation, right? Each coordinate transforms separately. So you do the same equation, and it's almost the same thing. The only thing that's changed is the sign of L over 2, right? So, therefore, when you calculate it, it looks almost the same, which means we don't have to duplicate all the work. It's going to look like this. The same thing, except that there's a minus sign here instead of a plus sign. Okay. Now, tell me, based off this, which bomb explodes in the Earth's reference frame? Which bomb explodes first? These are their 2 time coordinates. So which bomb explodes first?
The bomb on the right.
The bomb on the right, right? If you compare their time coordinates, all of these are positive numbers, which is good, so you don't have to worry about signs. So all these are positive numbers. So this is 1 plus something, this is 1 minus something. 1 minus something is less than 1 plus something, right? If it's all positive. Therefore, this is less than this, which means this is a smaller time coordinate. Smaller time coordinate means it goes first, right? So this goes first, then this. If you want to find the time between them, then I'll call this 2 and that 1 just so we can do it. Then the difference between them is L gamma over 2c times 1 plus b over c minus L gamma over 2c times 1 minus b over c, which is L gamma over 2c times 1 plus b over c minus 1 plus b over c. Make sure to get your signs right so you don't cancel the wrong thing. The 1's cancel, right? The b over c's do not. Instead, you get L gamma over 2c times 2 b over c. That's an L times 2. These 2's cancel, and you get L gamma b over c squared, which is not what I told you, right? Yeah. Okay, I don't know what I told you. This is right. I'm not really sure exactly where that came from. Yeah, I'm not sure. I'm not sure why I said that.
I wish there was a gamma symbol in.
There is on Google Docs.
What's the gamma symbol on Google Docs?
But you have all the answers that I have.
I don't know, is that true?
I have 4. I have 1.
I don't have one.
Okay, good. Other questions on the
0, 0, 0, 0.
Yeah.
And 2, 3c, 0, 0.
Think.
Yes. So Neil and Giscard. Anyone know that reference? A bit more obscure. No. No, it's fine. Neil and Giscard are characters from Isaac Asimov's robot novels. Isaac Asimov, science fiction writer, wrote a series of novels called the Thieves and all the robot novels. Neil and Giscard are 2 characters that wrote Asimov. Anyway. We had, so the main question I think that we need to solve for this one, because you have 2 of them blinking, and it says that they blink simultaneously. So if you set, this is Daniil on the left, right? If you set Daniil at 0, 0, 0, 0, his blink at 0, 0, 0, 0, and they blink simultaneously in this frame, then what does that mean? Giscard's time coordinate must be 0. Also 0. Simultaneously means the time coordinates are the same, right? His position, of course, is different. Then you have Jimbo's frame. But Jimbo is moving relative to that, right? In Jimbo's frame, therefore, what are they doing? They're moving which way? To the right? So, according in Jimbo's frame, this is what he sees, right? And he sees them blink simultaneously in his frame. And therefore, in the Neil and Giscard's frame, we have to transform to that. So, what would the sign of the velocity be when you're doing v for your transformation, right? Is it going to be a positive v or a negative v that you're looking at? Good. It should be the velocity of the Neil and Giscard, right? So that's what you're going into. The velocity of the Neil and Giscard relative to Jimbo, which is, and we said it's relative to Jimbo, they're moving to the right. So you should use a positive v, right? So you have a positive v, and I actually give it to you. It's 0.3. Is that it? Interested? Okay. So then from here, it's math. You want me to do the math too? Okay. Then from here, I think it's just a matter of plugging in, right? So people are all right. I'll stop there. Do you want me to keep going? Are we okay? Oh, that's loop.
Okay. So just really quick. So the answer to number 7 is talking about the 4 vectors in Daniil and Giscard's reference frame. So is that the 0, 0, 0, 0, 0?
So 0, 0, 0, 0 will still go through, right?
Yeah.
Then this one, the time coordinate and the position coordinate change.
Okay.
And there, I gave the numbers whatever they were, right? They were in terms of, yeah.
So for velocity, whether it's positive or negative, when you have the velocity of the rainbow, you're looking at the velocity of the
Right, it's always the velocity of the reference frame that you're trying to find out, right? The reference frame you're transforming into, in relation to the one you already know. Okay. So you're always sort of transforming into a different reference frame. That's the whole point, right? And so it's always the velocity of that target reference frame relative to your original. Okay. It takes a little getting used to get the sign right. Yeah. Sure.
The Greek letter for gamma is different than what we use for gamma.
Either I will tell you which origin to use, or more likely, I will ask you for an answer that is a physical answer that is independent of choice origin. In this case, the 4 vectors will be different, but what comes out the same? Who blinks first is still the same, regardless of your choice of origin, and the fact that the difference between the time coordinates is still the same. The difference between the spatial coordinates is the same. Those are independent of choice of origin. Okay, so those are all physically measurable. Good. More questions? Alrighty. Let us talk now about number 9. Number 9 is the first of a series of problems that we will be dealing with, which are designed to help your understanding of relativity. I find them very fun. They are often called paradoxes. It's a poor word because they're not actually paradoxes, but you might call them apparent paradoxes. Okay, the cookie problem is our first one. So, the most important thing to realize is why the problem is hard. Okay, the reason the problem is hard is because you can give 2 different arguments, both perfectly correct sounding, that give you 2 different answers that are physically different. Okay, can someone tell me what the 2 arguments are? Go ahead, John.
Because the sheet of cookie dough is moving at relative 6 speeds, it contracts in like direction. And then when the cookie cutter comes down, it cuts it in a circle at that speed.
Right.
But when it comes back to the normal speed, or the speed relative to the cookie cutter machine, then it stretches back out.
Okay. So that's one explanation, right? You can think about this, like a perfectly correct explanation. If you have trouble imagining a sheet of cookie dough moving at high speeds for some reason, but if you have trouble imagining it, you can help to sort of keep track of distance by imagining evenly spaced chocolate chip cookies, the chocolate chips going throughout here. Okay? Now, this thing gets contracted. So this is let's call this the lab frame. And this is the dough frame, right? In the cookie dough frame, it's stationary. What's moving? The particular one. The the cookie cutter is moving, right? The thing that actually wants the cookie to go up. Okay, good. So here's the thing. Here in the dose frame, let's say the chocolate chips are this far apart, right? Therefore, the labs frame, due to length contraction, you see the chocolate chips are therefore much closer together, right? Okay, now this thing drops down and cuts out a circle. Okay, good. So when it cuts out that circle, it has more chocolate chips in it than a circle of this size would, right? Okay, so eventually when you slow it back down carefully to the last frame, right, then it will return to what its length should be, right? And the length that it should be is longer because it has more chocolate chips. So basically the chocolate chips return to their normal spacing once you slow it down, right? It'll go back to the proper length, right? And if the chocolate chips returns to the normal spacing, then you're going to end up with a cookie that is spread, with the chocolate chips spread out, therefore the cookie itself must be elongated. And it can only be elongated in one direction, right? Because there's only one dimension of motion here. The other dimension is convective. So you get a cookie that is longer in the direction of motion. Does that make sense? Right? So that argument is completely valid. Great. That's not the problem. What's the problem? Someone give me another argument now. Let's do someone else. The Jacob.
If you're in the dose frame, then
Good. So in the dose reference frame, the cookie cutter does not in fact look like this. In the dose reference frame, it's a circular cookie cutter that is length contracted, which will mean it will look like what? A squish circle this way, right? Now, while it's flying by, it drops down and cuts out a cookie like this. And the result will be, and you're already in the dose frame, so you don't have to do any slowing down, right? There's no change, you're already in the cookie frame. The result will be a short cookie with fewer chocolate chips in it, less dough total. Okay? Now, this is problematic because at the end of the day, you will have a cookie in your hand. But that's not actually a promise. I'm only in the problem, not you. At the end of the day, someone can take this cookie and pick it up and look at it. And this is not the same cookie turned on its side. This is an extra big cookie, right? They have the same height, there's no change in the height, right? But this one is extra long, which means extra more dough and chocolate chips and other wonderful goodness. This one is extra short with the same height, right? So they are physically different from one another. Therefore, you cannot just say, oh, it depends on which reference frame you're in. No, you cannot. They are physically different outcomes. So this is what they sometimes call a paradox, or maybe you should say an apparent paradox, because it appears that in two different reference frames that you get two physically different outcomes that are measurably different from each other, right? And so when you had that problem, when whoever it was, I forget who we had going by doing jumping jack. No, juggling. Who was juggling? Was that Matt? We saw him flying by juggling. Who was this?
I was
dancing. You were dancing. Juggling was the other class. Okay, Matt dancing. He goes by. We saw him skinny, but then he saw us skinny, and that seemed weird, right? This is why. This is why it seems weird. Because it seems like, hang on, if that's true, then you end up with mutually inconsistent results for different reference frames. So, clearly the only thing to do is experiment. No, I'm just kidding. Yep.
These are both from reference frame, that's one of the reference frame of the cookie cutter, the other one's the reference frame of the dough. What happens if you're not in either reference frame?
Well, then you get something else, obviously. But that doesn't matter. You'll get something in between, presumably. But that doesn't even matter, right? The problem is that we have to resolve these two. You have another one, you have to resolve that one too, yes. But these are obviously the most relevant ones at the moment. Yeah.
Well, we defined this as they're either both right or neither. So I think in this case it would be neither reference frames are correct. So which leads to Benji's third reference frame.
Hey, hang on. The way you are thinking is a common one, and it's very important to realize that's not the right way to think, because you're trying to figure out which reference frame is correct, right? But according to Einstein, which reference frame is correct?
All or neither.
Right?
Or none.
All reference frames are equivalently good in Einstein's formulation. So you can't say, oh, this one's right, this one's wrong, or they're both wrong. It's not about being right or wrong. Whatever happens physically must happen in every reference frame. Okay? So you can't say this one's wrong and then just ignore it. No, no, no. You have to explain to me what happens physically in both reference frames that will give a physically consistent answer. Okay, so it's not about right or wrong frames. Yeah.
Okay, so at the for NT1 in the time frame of like a slowing down, that's what at the end when it slows down. So
Ignoring the fact that
but like
eternity does.
we're saying that like it's the cookie cutter looks around in the time frame of the cookie cutter. So we need to like do like the Lorentz transformations to like turn that like so like, if we set the cookie cutter, if we like set like both ends or something, that like when you turn it into the last frame, that like one end's gonna come down.
Right. Okay. So let's. Here's what it is. It is in the end a problem of, like Alice was saying, Alice, right? A problem of simultaneity. You're like, what? Simultaneity. There's only one thing happening. But keep in mind, what is an event? An event has a time and a place. So tell me, the cookie cutter comes down. That has a time. That's pretty easy. Where does it happen?
On
On the cookie, you say. But where on the cookie? Here, here, here. The cookie is an extended object. Thus, the cookie cutter coming down is not one event, but a series of events. Cutting the cookie dough here, 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 because they happen at different locations. They happen at different locations or different events. You see what I'm saying? Well, let's see what happens as a result of that. That is to say, let's just simplify and look at particularly cutting the cookie dough on this side and cutting the cookie dough on that side. Okay? Well, let's assign some coordinates here. So where would I put my origin?
the one on the right.
Let's do the one on the left, please, because I don't like negative numbers. So the one on the left I'll call 0, 0, 0, 0.
You're gonna have to deal with negative numbers, not you, because of negative time.
There will be negative signs no matter what, I understand that, but I'd like to avoid them for as long as I can. Over here on the right,
Me with the
this one, let's say the width of this is D for distance, sorry, for diameter, for diploma, or
Dancing.
drums.
Dead on the inside?
Anyway, so in this frame, in the labs frame, it tells you specifically, if you read it, in the labs frame, what's the time coordinate of the other end. Also 0, because it says it comes straight down, boom, right? Which means that both sides will hit at the same time. So this will be 0. What will be the position coordinate? D. Okay? See, if you think about it this way, they have to be the left end and the right end, and also everything in between, but we'll just focus on the far ends. The left end and the right end have to be different events. See, they have different coordinates, which means they transform separately, right? Okay, furthermore, you know that these events are simultaneous in this reference frame. What does that tell you about other reference frames?
It's not going to be simultaneous.
Not simultaneous in the other reference frames. Ooh. Let's see how that works. By the way, how long would this cookie be? By factor, it would get longer by factor of gamma, right? This would be L gamma, right? That's that we're comfortable.
D gamma.
D gamma.
The gamma.
Should do variables. Okay, so now let's transform over into this reference frame. This, of course, this prediction is D over gamma, right? Okay, that's that. It's just like contraction going in two directions. Okay, now let's look at this reference frame. Okay, this one, of course, becomes 0, 0, 0, 0. Because the origin never changes. Now let's look how this one transforms. T prime equals gamma T minus B over C squared X. So gamma times 0 minus B over C squared D. Or negative B D gamma over C squared. By the way, you'll notice it's very similar to that one over there. Velocity is in this direction, so velocity is positive. Okay? So what does that? What do you notice about the time coordinates here? They're not the same as promised, right? Which one happens first?
The one on the right.
The one on the right happens first. So that means the cookie cutter in the nose reference frame does not come straight down. The one on the right has to hit first. and then the one on the left. Furthermore, let's look at x prime. Let's find the position coordinate. So x prime is gamma times x minus dt. So that's gamma times our x coordinate is d minus b times 0. Give me a position coordinate of
Gamma D.
Gamma d. A longer cookie.
So the longer cookie is the correct
So
cookie?
it's a longer cookie. That's exactly what the Lorentz transformations predict. So our 4 vector here is negative ED gamma over c squared, gamma d, 0, 0. And the gamma d tells you that the length of the cookie, because the length of the cookie is defined by cut at one end, cut at the other end. The distance between those is the length of the cookie. In the Doe's reference frame, it's the length of the cookie, right? And it comes out to gamma d, exactly in line with this prediction, right? And the time coordinate is what is off. Okay, so it's not a matter of which reference frame is right. All reference frames are right. But one of our arguments was wrong. Okay? The argument that was wrong is in this reference frame. What was wrong with our argument?
You're saying both events happen
We
simultaneously?
assumed that the cookie cutter would come straight down like this in both reference frames. Turns out that's impossible. I know, right? Weird, right? Because if it comes down straight down in this reference frame, then you get simultaneous events. Therefore, in another reference frame, you get non-simultaneous events, which means, what, in addition to being length contracted, what does the cookie cutter look like?
It's slanted.
It has to come down at an angle, right? Furthermore, then when it hits, what has to happen?
One side like
It has to like twist and like roll around like this, but still squished, right? So this tells you that the cookie cutter cannot stay rigid. That's to say, its shape it can't stay perfectly in that same shape, right? It has to kind of twist and bend in order to make this thing work. This is true. So, in order for this to work, we have to conclude a few things. One is that shape is relative. We already knew that, actually, right? The circle becomes an ellipse. That wasn't so bad, right? But the other thing is, in relativity, there is no such thing as a rigid object. A rigid object is an object where 2 parts of the object are always the same distance from each other. Or the same distance and like orientation from each other. And that is not possible in relativity. Simply not possible. Every object that is extended over a range has to be allowed to twist and bend, or else the relativity fails.
Can you go over what you would find if you started in the Doe reference?
Sure. That's a good exercise. What if we start in the Doe's reference frame? Well, that's a little tricky. What's the question? You mean if it goes down, straight down in the Doe's reference frame?
Yeah.
Okay, so that's a different question now, right? Okay, so that's a good exercise. We can take a look at it. So Timothy's asking about a different question. What happens if instead of, I told you this thing comes straight down in the lab's reference frame. What if instead it came straight down in the Doe's reference frame? Okay? Well, then what you would have is, you would have your cookie, this is the Doe's reference frame, right? Let me draw it. You would have the Doe's reference frame, it's not moving. You have the cookie cutter, which is moving, and it has a length of d over gamma, right? Because it's length contracted, okay? It's moving at a velocity d this way, okay? Then it drops down, and it will cut out a cookie, and we'll have two events again. If they're simultaneous in this frame, the left-hand one will be 0, 0, 0, 0. The right-hand one will be 0 still, because I told you it was simultaneous in this frame. Then d over gamma, 0, 0. Okay? Now, here though, to make this a little bit clearer, I'm going to say that the velocity we use, because the cookie cutter's frame is moving to the left relative to the Doe, that means we should be using a velocity of negative v. I like to keep my v positive and put the negative sign on the outside, just to make it clear. You see what I'm saying? Because the velocity is definitely going that way. Okay? So now we do our transformation into the lab frame. In the lab frame, which is with a moving cookie dough and a stationary circle here. Okay. In the lab frame, of course, the origin remains the origin. When we pull this down, our time coordinate is gamma times 0 minus negative d over c squared d over lambda, which is therefore that's d over lambda, right? Oh yeah, it is d over lambda, right? So lambda, the gamma's gamma's canceled, so you get positive bd over c squared. X prime is going to be gamma times d over gamma minus negative b times t, which is 0, so that gives you d. Okay? And then what do you see in this frame? You see, again, the twisting cookie cutter, right? Where which side hits first?
Right.
Here, let me write out the coordinates. So this is dd over c squared d 0, 0. Okay? Now this
it's the left one that hits first because it's
the left side, 0 comes before a positive number, right? So the left side hits first, then the right side. So that means it looks like what? That means it comes down like this, lopsided, right? And then it hits the left side, and then it's the right side. And sort of twists around in between, right? But when it does it, what kind of cookie does it create?
the short
A
cookie.
circular cookie, right? The size D. I mean, this is rated with D, right? In exact accordance with what you expect, because here's the length contracted version, and here's the uncontracted version. So this is a different problem, right? That I'm doing this is an example to try to show how the Lorentz transformations work. Sir.
So if you use d instead of d over gamma, then we just get d gamma.
If it were circular in this reference frame, that would mean it would be all elongated in this reference frame, which would be d gamma, therefore. So, what do you think? Do you believe me? Well, I can understand. As scientists, you should be skeptical without experiment, right? Good. So let's do this as a lab. Who here is allergic to nuts? Excellent. So, for your lab,
You
come here and take a piece of lab equipment. One per person, please. And then you can see for yourself that the cookies are in fact elongated in the rest of the
How are we going to accelerate
Just one each, please.
Are we going to accelerate
What if they were like this?
I didn't know if we were actually recording an experiment.
What? How are you going to get a cookie to move at relative speed in the middle of a high school?
I asked this question as well. Would this be plenty of cookies? Hold on, can we see this effect in photons?
Shut up right now, okay? Let's not get into photons.
Can we see this effect in particle accelerators?
Yes, let's tell CERN to make a particle accelerator for cookie dough.
What would happen if a cookie went at
That's not what I'm
relativistic
saying.
speeds? Wouldn't it just disintegrate?
What?
If a cookie went at relativistic speeds, wouldn't it just disintegrate?
No.
It would just
It's
go
the
really, really
acceleration that's the tricky part. Getting it to relativistic speed relative to you is hard. Once it's going at the speed, it's fine, right? Yeah.
It wouldn't disintegrate if there's no force going against it.
No, the Einstein should have. You can see by looking at these things, they have a gamma factor of approximately 2, right? Meaning that
Unless you look at from an atom
speed of the
structure
conveyor belt was approximately 0 to 2c. Which is about what I said it to. Last night. So, now I think that we're confirmed beyond all shadow of a doubt that this is how things work. We can move on to other things. Okay.
Let's get one.
That's like, wait a minute, we can make sure this is reproducible. So,
You know, more trials is better for your experiment.
Yeah, exactly. Yeah, large sample size is essential. It'll turn you into a large sample. All right, so let me talk about, we're not going to try to do velocity today. We'll do that next time. Let me instead talk about an important problem that is actually an Einstein original. A lot of our stuff is actually Einstein original. Einstein was for a physicist, remarkably good at explaining himself, clearly. Not so much to maybe not to the random dummy on the street that they find in the little, you guys have the Jay Leno, you don't have the Jay Leno thing, so you guys don't even know that random the street thing anymore, do you? No. Okay. Hey, Jay Leno, do you know who that is? No. Yeah. Well, Jay Leno used to do this segment where you go around, I think, New York, and ask people simple questions and then tape them, and then it would show how good they are. Oh, yeah.
Billy on the street.
That's still okay, good. It's always good because you just, you make people say stupid things and then edit the videos, make them look extra stupid, and then it's great, everyone.
What'd be really funny is if they did that and they accidentally asked a genius in the world.
Yeah, but then they just
wouldn't show them.
They wouldn't admit that there are smart people.
Yeah.
They only profit
Right, yeah,
a few really bad responses.
Okay. So anyway, no, Einstein was not so good at necessarily at just editing one, but someone, a student, someone with a studious mind who knows some algebra. Einstein actually came up with a lot of things that he wrote that explain things clearly. And one of the classic ones is what is usually called the twin paradox.
Oh boy.
Oh.
So that's right. Who we used twins last time? Right? Oh, did we use the other twins? Yeah. You have a twin too? Who's your twin? Eva? Okay, so Alice and Eva. Okay, that works. Here's the twin paradox. Some of you have already thought of this, because I implied it at the beginning. And some of you may have already read the solution, in which case, keep your dumb mouth shut. Because the important parts of these things is not knowing the answer, but trying to figure it out, because that's where you learn more about what you know and don't know about relativity. Okay? So here's the twin paradox. Let's say that Alice, you want to be younger or older? You want? Okay. But I mean, what do you want to be though? Okay, got it. Okay. So Alice will be standing here on the Earth. She's very big, which is really Earth's right. And then this is Alice. And then Eva, who's probably going to be slightly smaller, is on this large spaceship. Okay? And Eva goes the spaceship very, very fast. Just for sake of arguments, let's say gamma factor 4. Okay? She goes away, she turns around, comes back. Here we are back at Earth, and Alice and Eva are standing next to each other. Now, for Alice, let's say that this trip, the elapsed time of this trip is 20 years. For Eva, if she looks at Eva, therefore, she should see the elapsed time of
Not 20 years.
If she's looking at Eva, she should see that if she watches Eva's clock, right? She should see for Eva the time elapsed should be 5 years. Good. Therefore, when they come back, as we discussed, Alice is 16, 17, 15, I'll hold the change here. So Alice is now 35, right? At this point, she's well on in her career, maybe married as kids, I don't know. And Eva comes back, and Eva is 20, right? And so they meet each other, right? And they meet each other after a number of years, an unspecified number of years. They meet each other. It's been a long time. They shake hands, and when they shake hands, anyone watching them can agree which one of them is older, right? One of them will look like a college girl, and one of them will look like a woman approaching middle age, right? And there are biological differences between them that can be measured by anyone and agreed on by anyone. So, okay? And that was the part. Okay, that's not a paradox. That's just kind of weird. Here's the paradox part. What about Eve? From Eve's point of view, Eva. There's a movie called All About Eve, and I got confused. Okay, Eva is on the ship, and according to her reference frame, what happens? The Earth goes this way, comes back, right? So, so Alice is now on the Earth, and according to Eva, how long has elapsed? Well, Eva hasn't been moving, the Earth has. So for Eva, it should have been 20 years, and for Alice, it should have been the contracted 5 years. And now they are next to each other, and Eva is 35, and Alice is 20. Now, once again, they are standing next to each other, and any observer can agree, including themselves, can agree that one of them is older, right? So they cannot both be right. Yeah, I mean, if you really want to be macabre about it, you can make it a much longer trip, and then one of them's dead. Okay, so the question is, so again, remember, it's not a question of which reference frame is right. Reference frames are reference frames, right? It's a question of where is there a flaw in our argument?
Wait, did Einstein create this paradox and then solve it instantly?
Yeah. Someone else may have asked it to him, I'm not sure. Eva's not moving. Her reference frame.
Or the time like the first. No, it's like in the first reference frame, right? Like Alice is observing 35 years.
Right.
But in Eve's reference frame, that time is shorter because she's moving faster.
She's not moving. In Eva's reference frame, Eva's not moving. Alice is moving at the exact same speed that Eva is moving in Alice's reference frame. And even if you say, well, it should be 5 here, well, okay, but this is something shorter than 5, right? It's still the same problem, one's older. Okay, Kristen.
What is it? That there's like acceleration definition. It's like there's a change in velocity.
Change velocity where?
There's a change in gravity.
Okay, good. In which reference frame is there a change in velocity?
In which reference frame does anyone
It's
know?
like both, right?
Yeah.
Okay, so you say that the change in velocity of both. But is that really true? Well, why? If it's an inertial reference frame, it can't change velocity. Okay, true. But it looks to me like they're both changing velocity. They both turn around.
Yeah.
So how do I know? You say, okay, so let me start our experiment. We said special relativity only applies to inertial reference frames, right? If there's acceleration happening, it is not an inertial reference frame. If it's not an inertial reference frame, then the laws that we derive do not apply. We've been assuming constant velocity. Okay? So you know what? That is actually the solution. But which one of these is an inertial reference frame?
None of them.
How do you know? Okay, what do you think, John?
I don't know.
Oh, great.
I wasn't thinking.
Okay, that's fine.
Because shouldn't you be able to detect acceleration? Like, because you can't, there's no certain reference frame for an inertial reference frame. There's no special reference frame. But for acceleration, you should be able to measure acceleration.
Okay, how do you measure acceleration?
With,
Velocity over time.
Okay, good. So acceleration is actually detectable because you know that acceleration always leads to is always related to a force, right? There's something that, right? And here you have things that we call fictitious forces. For example, when you are, you guys ever go subway surfing? I guess in Chicago it's L surfing. You know what I'm talking about? Yeah, right? Subway surfing is when you stand on the subway or the L, right, and try and stay standing without moving your feet, without holding on to anything. Right? And you want to do the right way to do it that's extra hard is to face forward, put your feet together, which makes it much harder. And then you have to stay standing without a stop. It's kind of fun as long as there's no one else around you because you're likely to smack them. So don't do it with like a crowded subway. It's not nice to people around you. But an empty subway is pretty fun, or L. Okay, anyway, when you're subway surfing, right, if your eyes were closed, Would you be able to tell when the thing stops?
Yeah.
Yes. How? Because you fall forward. Okay. From your perspective, what happens to you?
The floor.
Yeah, but really, what happened to you?
You
You fell which way? Forward. There was a force that pushed you forward, right? We call that a fictitious force. There is not actually a thing on you that pushed you forward, right? But it feels like it. What actually happened was the car slowed down. You were still moving at the same velocity. The car slowed down, and then you and you were still going the same velocity, which provided force on your feet by the floor, which pulls backwards, making you fall forward. Okay, that's what we say what really happened. There's no such thing as what really happened anymore, right? We're talking reference frames. Both of your reference frames are valid, but one of them has this fictitious force in it, as they call it. And a hallmark of accelerating reference frames is fictitious forces. That you have forces that are not well explained by anything else. Okay, so in the case of the fictitious force, you know if you experience such a thing, a force that comes from no other explainable reason, then you know there's acceleration happening. So you can actually measure and agree on whether there's acceleration happening. Let's imagine Eva turns around really fast. Okay? If she's standing there in the ship, and the ship turns around suddenly, what's going to happen? She's going to be like, ah, right? Okay. On the other hand, in this point of view, when the Earth turns around, does Alice go like flying off the Earth? No, right? So there is a measurable difference, a physical difference between these two situations, right? The main thing is this: the Earth and the spaceship are not symmetrical, right? They are not. I set it up to make it seem like they're identical, that they're just symmetrical situations. But in these problems, they're never symmetrical. There's always something that makes them different.
If it's been 20 years,
and that something is where the paradox is always hidden. And here it's because this spaceship turns around, which will cause a force to be on it. That force is not felt on the Earth. And thus you can distinguish between the two frames. Okay? There's actually a lot to the twin paradox, and you can think about it for quite a while, and maybe you should. It helps deepen your understanding of relativity. Sir? And define a fictitious force. A fictitious force is a force that comes not from the results, not from the action of one object on another, but from the acceleration of a reference frame. Okay. We deal with them all the time, mainly in cars, but there are other ones. There's one called the Coriolis force, that comes from the rotating Earth. You guys ever seen a Foucault pendulum? There's one in the Museum of Science and Industry, a giant one, right? The big ball on the big string at the top, and they have the dominoes at the bottom, or whatever. You guys know what I'm talking about? Yeah. If you don't, this is the museum. Find that stairwell. Let's go down one of the stairwells.
It's also in the store. Yeah, that's
right. Oh, so the store's in it now? Okay, good, which is fine. I've actually been there for a while. I used to go all the time. It's such a great place. It's a pendulum, swings back and forth. Basically, it's on a very carefully designed mount, so it swings back and forth, and as the Earth rotates, it stays still, so the Earth rotates underneath it. And therefore, you can see that it swings off a different path over the course of the day. And it's pretty cool. They have stuff at the bottom so you can see the path it's been making and how it's been turning. It's pretty cool, but from the standpoint of us, there's a force that is causing it to twist, right? That force is called the Coriolis force. It's a fictitious force that comes from the fact that the Earth is rotating. And that we're in a rotating reference frame on the Earth. Yeah?
So would like an example of that be like when you're bowling and then like the ball turns like it?
No, that's spin. Okay. That's just spin. Like say it's in any sport that it's tennis or something. But it's when an object rotates this way that's a frictiony surface, then there'll be a force that forms on it, which will cause it to change the direction. The Coriolis force, this fun thing is, any of you guys have an old playground that has those old things they don't allow you to use anymore because they kill the kids? That's like a big, we just call them merry-go-round. They're just rotating right? They're made of sharp metal, just so as to better kill kids. There's something like a death go-round. Okay, they don't put them on playgrounds anymore, but like, they're so much fun.
Yeah.
Right? The reason they don't put them on playgrounds is exactly the same reason that they are so much fun. Because you go around really, really, really fast and then like jump off or something. But if you never did that, one of those, a really fun thing to do is get on it with a friend and get it going pretty fast, okay? Then get a basketball and stand at opposite ends and try and toss the basketball to each other.
Oh, God.
It is really fun. You can try rolling. Well, I mean, usually it's a thing in the middle, though. Well, that's the problem sometimes. Yeah, if there's not a thing in the middle, you can roll it, yeah. But if you do it, it's really fun. Because here's the thing, you're in a rotating reference frame at that point. Because the Coriolis force is only rotating that fast, and then you're that close to the center, is very strong. And so from your perspective, you're going to like, it's like, okay, I'm throwing to the nay right here, and you throw it, and the ball like goes, and it flies outside. And from the perspective of someone else watching, it's even more fun, because for them, everything's going, they're not rotating reference frames. Everything goes in a straight line. So they see you just go like, wow! Way off. What are you doing? Great, that's that.
What happened if you spun the ball in the opposite direction?
If you spun the ball, it would not help. There's nothing for it to get friction off of. If you like, I guess if you're rolling it this way, you get a reverse spin, that would work. You can get it to go like that. But yeah.
Realistically, if you're going fast enough, do you think you could throw it to yourself and you come around on the other side?
It's possible.
You're getting a very nice.
Now you can hit yourself in the face.
New game.
You have to be going fairly fast. But no, I mean, you got one of those. Yeah, you got a ball.
That's not kind of what she was talking about, Kimura.
Grab a car and change it and run around.
They're so much fun. I love those things.
Let's go. Take out Dr. Dong. Let's make it a field trip.
Well, yeah, you can. Those actually pretty good airtime, so you can probably do it at one of those.
Wait,
And Foursquare.
that up,
I don't know if
man?
Foursquare-
It's a lot, actually.
have a laptop.
What?
Look it up on the laptop.
So, for your homework, what I want, I'll give you for your homework.
Is our homework going to play on a merry-go-round?
Yes.
I can't require that because it'll require you to put your life at risk.
Going to the school has put my life at
I
risk.
know, right? Now that's much easier.
Okay, technically anything puts our life at risk.
Exactly.
Problems related to the inverse of the twin paradox. It's not a paradox. Inverse of the twin paradox is just the twins, I guess. And plus, you know, I give you the tardy student problem. That was always fun.
We're done?